Last session, we stopped here with MUNIT. It's a multimodal unsupervised image-to-image translation framework. And you're going to be using generative adversarial neural networks for it. And the most important component was this adaptive instance normalization, in addition to the way that you're going to be separating style from content. So a good way to model style is using adaptive instance normalization, where you have this gamma and beta. You can play around with it, and perhaps condition it on another image. Okay, perfect. Let's see another application of GANs. This one I covered last year, so I'm not going to spend too much time on it. The video is online. You can watch it. It's actually an assignment to watch that. And the idea is super resolution. In part one of the course, we spent a lot of time doing super resolution. And over there, we were not using GANs at all. And everything was deterministic. The images that were coming out were all deterministic, and they couldn't imagine the details or start imagining tiny details of your images. With super resolution GAN, you can actually do it. Many of the ideas in this paper are actually the ones that we cover in part one of the course, such as rather than using mean squared error as your content loss, this is the mean squared error between the high resolution and the super resolved image. Rather than using mean squared error loss, which is going to give you blurry images, you can actually use a deep neural network to give you the corresponding loss function. VGG is a pre-trained neural network on ImageNet data. It's for classification, but you can cut that neural network at some layers, look at the features or the feature maps at that particular layer, and then compare the features rather than the images. Basically, you're comparing at the feature level rather than comparing your images at the pixel level. MSC is doing it at the pixel level. Loss of VGG is doing it at the feature level, and the features are coming out of a VGG pre-trained network. Your loss function could give you the content loss here. A VGG network can give you the content loss. And there are actually some very good systematic studies that there is high correlation between what pre-trained deep neural networks think the content of an image is and what a human being thinks the content should be. There we cover those sorts of paper in part one of the course. But so far, everything is from the past. We know that we can use VGG network to give us the content loss. We know how to design a neural network, taking as input a low resolution image and output the corresponding super resolved image. We spend a lot of time designing the architectures in part one of the course. The new addition is this adversarial loss. And this is going to introduce some stochasticity into the generated images. And then that way you're imagining some fine details of the generated images. And the adversarial loss, you're going to have a discriminator, which is going to help you train your generator. And in this case, your generator is basically the mapping or the function that takes you from a low resolution image to a super resolved image. That's your generator. And the discriminator is going to discriminate between real and fake. And the generator is going to try to make the discriminator make a mistake. This is the actual formulation of the loss that is going to go in here. And for the task of super resolution, there aren't many good metrics because it's a creative task. And once you lose your resolution, you lost it forever. It's very hard to recover it. And it's going to end up being a qualitative metric in the end. You're going to show it to a human being and say, this looks good. But we cannot use human judgments all the time. And there are these three metrics that exist these days. Or you can actually use a fourth metric, which is going to use a pre-trained neural network to give you an evaluation metric. Peak signal to noise ratio has a strong correlation. If you look at its formula, it's basically your mean squared error loss with some additional terms. So there's high correlation between MSE and peak signal to noise ratio. If you minimize your MSE, you're going to get a high peak signal to noise ratio, but that is not necessarily a high quality image. It might end up being blurry and it still give you high peak signal to noise ratio numbers. That's why that's also an active area of research. What is the correct metric, or what is a good metric here? Any questions?
Hi, sir. I had one question. So, in many of the, at least the papers in super resolution, what they do is they have like a high resolution image, and then they generate the low resolution image using some sort of interpolation method, and then they train it. Is that like a correct approach? Because what the model ends up being learning is basically the mapping, right? The interpolation method specifically.
So yeah, this is something that I forgot to mention. Thank you for bringing it up. For the task of super resolution, you can generate as many data points as you like. You can take your original training data, which are going to be high resolution. You can push them through a Gaussian filter, downsample it, and then that's going to give you the corresponding low resolution. Well, there are actually other ways of coming up with low quality images. For instance, if you have this image and you encode it as JPEG, you're going to lose some information, and that could be your low quality image. And there are actually multiple ways of doing it. And this task of super resolution, it belongs to a larger class of problems where you are mapping an image to another image. So this is actually in the same category of problems that we were covering from image to image translation. Another task is you want to know the depth of an image or the depth of objects in an image. That's going to be called depth estimation. That one we cover in part 1 of the course. Semantic segmentation is another one. Flow estimation, optical flow is another one. These have applications in robotics and self-driving cars. Those we cover in part 1 of the course. But you're right, we can generate as many data points as you like. But then it also matters. For instance, it matters what is your downstream task and what is your downstream product. For instance, you can do ray tracing. For ray tracing, you are going to reverse the way that the light works. Usually we see objects because there is going to be a light source, let it be sun or a lamp. It's going to eject a ray. It's going to hit the object, and that ray is going to reflect and hit our eyes. For ray tracing, you're going to reverse that. You're going to say our eyes are the ones that are emitting rays, and then it's going to hit your object, and then you can see it. So it's a smart way of reversing how the light works, how the physics of the light works. But then it's going to end up being extremely costly. You're going to need to eject a lot of rays to be able to see the actual 3D object and be able to actually visualize it, render it on a computer screen. And this is actually what happens behind the scenes whenever you're playing a game or whenever you're watching a video, watching a movie. It's going to be based on this ray tracing idea, especially the animation ones, animated movies or games. For animated movies, you can afford to use a lot of rays. With real-time gaming environments, you're not allowed to, or you cannot afford to use a lot of rays. Therefore, what is the moral of the story? The image that you're going to end up with is going to end up being noisy. There's going to be the image of this person with a lot of noises. And denoising is another application, and it belongs to the same category of image-to-image translation. So to answer your question, you're right. For super resolution, this is what people use. But then if you change your application, you're going to be thinking of different ways of coming up with pairs of images, input output. Okay. Did I answer your question?
Yeah, thanks.
Okay, perfect. Any other ones?